Good morning, students. Today we are going to talk about monitors concept. Last class we have studied about process synchronization. Generally, this process synchronization is in second unit, second chapter. In previous class we have studied about process synchronization, see how process synchronization works, and at the same time what is a critical section problem, see what is the syntax for critical section problem, and at the same time what is the four essential elements of a critical section. Okay, major elements are entry section, critical section, exit section, and remainder section. Next, one more thing is solution to the critical section problem. If you find any solution, that solution must satisfy the three conditions, that is mutual exclusion. Next one is progress, finally bounded weighting. Next one is Peterson solution. See, generally Peterson solution is the software based solution to the critical section problem. Next one is how we are going to solve the critical section problem by using Peterson solution, by using two shared variables. Next one is synchronization hardware. Next one is mutex log, just like as a querying log and releasing log. Next one is semaphore. In this one majorly we are going to use two operations, that is wait and signal. So the next one is what is a wait, what is a signal. Next, properties of a semaphore, types of semaphores, advantages of semaphores. Next one is the classical problems of synchronization. First one is bounded buffer, or we can say producer consumer problem. Next one is dynamic philosopher problem, readers writers problem. Okay, so all these topics covered in previous class. So next, today we are going to talk about monitors. Okay, so generally what is a monitor, how we are going to implement this monitor. So generally the monitor is one of the ways to achieve process synchronization. Okay, if you want to achieve process synchronization, we are going to use the concept called as monitors. See, the monitor is supported by programming languages to achieve mutual exclusion between processes. Okay, generally this monitor we are going to this monitor is supported by the programming languages in order to achieve the mutual exclusion between processes. Okay, monitors are abstract data types. We can say these are the abstract data types and contain shared data variables and procedures. The shared data variables cannot directly accessed by process. That means those shared variables, so it cannot access directly by the process, and the procedures are required to allow a single process to access the shared data variable at a time. Okay, so next one is what is the syntax of a monitor. Okay, we have here monitor name, next we have variables, next to procedure 1, next to procedure 2, and procedure 3, and so on, procedure and n number of procedures. Next one is initialization code. Okay, it is a collection of condition variables and procedures. Okay, we have variables and procedures combined together in a special kind of module or package. Okay, here we can say it is one package. Here what we have in the package, collection of condition variables and procedures, both combinedly in one place. Okay, the next one is the process running outside the monitor can't access the internal variables of the monitor but can call procedures of the monitor. It means the processes which are running outside the monitors, okay, those processes, they can't access the internal variables, that is data variables of the monitor, but they can call the procedures. That means here procedure 1, they can, the process which is running outside the monitor, they can call the procedure P1, procedure P2, procedure P3, but they cannot access the variables, that is data variables. Only one process at a time can execute code inside the monitor. Okay, in this monitor only one process at a time can execute code inside monitor. Okay, so this is the concept of monitor. Okay, so next one is only one process can active in monitor at a time. In the monitors we have only one process, it will be in active position. Other processes that need to access the shared variable in a monitor have to line up in a queue and are only provided access with the when the previous process release the shared variable. Here conditional variables are, we are going to use two conditional variables. First one is weight and the second one is signal. Okay, two different operations are performed on the conditional variables of the monitor. First one is weight and the second one is signal. These two are the operations. Okay, so let us say we have two conditional variables now. So first one is condition x comma y. These two are the declaring variables. So here what will happen is weight operation and signal operation. X dot weight, it is nothing but process performing weight operation on any conditional variable are suspended. The suspended process are placed in block Q of that conditional variable. Okay, whereas x dot signal, when a process performs signal operation or conditional variable, one of the blocked processes given chance. These two are the variables, conditional variables that are used in monitors, x dot weight and x dot signal. So next one is synchronization examples. See what is meant by how we are going to performing the synchronization in different operating systems. Okay, see if you see the operating systems of Solaris and Windows XP and Linux. Okay, so how we are going to perform achieve the synchronization in Solar operating system, how we are going to achieve the synchronization in Windows XP operating system, how we are going to perform the synchronization in Linux operating system. Okay, as we know, Solaris is one of the most important operating system. So implementing in this one, we are going to implement a varieties of locks to support multitasking or multi-threading, including real-time threads and multiprocessing. If we want to lock, we are going to use different locks to support the multi-processing or multi-threading. Okay, see for example, if you want to implement multi-processing, then we are going to use different types of locks. At the same time, if we are going to implement multi-threading concept in Solaris operating system, at the time also we are going to use different locks. Okay, either acquire lock and at the same time release lock. Okay, in this one we are going to use adaptive mutexes for efficiency when protecting data from shortcode segments. Okay, here we are going to use mutex called adaptive mutex for efficiency. Okay, at the same time we are going to use conditional variables and reader writer locks when the longer sections of code need access to data. Okay, so at the same time we are going to use turn tiles to order the list of threads waiting to acquire either a adaptive mutex or a reader writer lock. Okay, in this Solaris synchronization mainly will focus on the logs and at the same time adaptive mutex for efficiency we are going to use. Next we are going to use conditional variables. Next we are going to use a turn tile to order the list of threads. Okay, all these are the various types we are going to perform in the synchronization in Solaris operating system. Okay, so next one is how we are going to implement synchronization achieve synchronization in Windows XP. Generally, Windows XP is one of the most important familiar operating system nowadays we are using. We are going to use this interrupt masks to protect access to global resources on uniprocessor system. Okay, in this one we are going to use interrupts mask. Okay, at the same time we are going to use spin locks on multi-processor systems. Okay, and it also provides a dispatcher object which may act as either mutexes or semaphores. Okay, so in this way we are going to provide the synchronization in Windows, whereas in the Linux also we are going to achieve the synchronization by using semaphores and spin locks. Okay, in this way we are going to provide the synchronization in various operating systems like Windows and Linux and Solaris operating system. Okay, here the major important questions are, if you see the examination point of view, the major questions are classical problems of synchronization, that is dining philosopher problem. Okay, and next one is the reader writers problem. Okay, see the major focus on dining philosopher problem is another problem of synchronization. Okay, generally in this dining philosopher problem we have 5 philosophers sitting around the table, in which there are 5 chopsticks or we can say forks kept beside them and a bowl of rice in the center. In the center we have one bowl, in that one we have rice. At the same time, 5 philosophers are sitting around the table. When a philosopher, what is the work of philosopher is? When the work of philosopher is whether the philosopher can eat or the philosopher can think. Okay. When a philosopher wants to eat, he uses two chopsticks, one from the left and one from the right. When a philosopher wants to think, okay, he keeps down both chopsticks at the original place. Okay. Here, whenever a philosopher wants to eat, at the time he uses two chopsticks for eating purpose. Okay. So here at the same time, if you see the representation of the dining philosopher, here the problem statements are consider the 5 philosophers. Here philosopher P1, philosopher P2, philosopher P3, philosopher P4 and philosopher P5. Okay, sitting around the circular dining table. Here we have circular dining table where the 5 philosophers are sitting around the table. The dining table has 5 chopsticks, or we can say 5 forks, and over here 1 fork, 2, 3, 4, 5, 5 forks and a bowl of rice in the middle. Okay, this is a bowl for P1, this is the bowl for P2, this is bowl for P3, philosopher P3, this is the bowl for philosopher P4, this is the bowl for philosopher P5. Okay, for example, this philosopher P1 wants to eat, he should take either his left side fork and right side fork. Okay, so this is the problem statement of the philosopher, dining philosopher. Here the major thing is at any instant a philosopher is either thinking or eating. Okay, the major work of the philosopher is eat or think. When a philosopher wants to eat, he uses 2 chopsticks, one is left from one is right, and when a philosopher wants to think, he keeps down both the chopsticks. The solution is, from the problem statement, it is clear that we came to know that philosopher can think for an indefinite amount of time. That means for example, he wants to think means he will think indefinite amount of time. We can't say when he will finish his thinking. Okay, but when a philosopher starts eating, he has to stop at some point of time. Why? Because he can't eat more rice. Okay, that means there is a limit for the rice. Okay, whereas there is no limit for the thinking. Okay, the philosopher is in endless cycle of thinking and eating. Okay, see here next to, when a philosopher wants to eat the rice, he will wait for the chopstick at his left hand, pick up the chopstick. Okay. At the same time, then he wait for the right chopstick to be available and then picks his two. After eating, he puts both of the chopsticks down. Okay, but if all the 5 philosophers are hungry simultaneously, okay, what will happen? And each of them pick one chopstick, then there is a situation called a deadlock. Okay, deadlock occurs because they will be waiting for another chopstick forever. Okay, they don't get the another second chopstick. Okay, the possible solution for this are a philosopher must be allowed to pick up chopstick only if both left and right chopsticks are available. The solution for this deadlock is only whenever the philosopher feels hungry, then only he first of all he will check whether both his left and right chopsticks are available or not. Okay, whenever a philosopher must be allowed to eat only if both left and right chopsticks are available. Allow only 4 philosophers to sit at the table. That way, if all the 4 philosophers pick up 4 chopsticks, there will be 1 chopstick left on the table. So one philosopher can start eating, and eventually 2 chopsticks will be available. In this way, we are going to avoid the deadlock. Okay. So this is the problem of dining philosopher. Okay, so dining philosopher problem. At the same time, there is one more problem is a producer consumer problem. Okay, in this one we have what is a producer consumer problem? We have here producer, and we have here also we have consumer. There is 2 different processes. A producer is one process and a consumer is one more process. Okay, so here we are going to use a buffer for producer and the consumers works, we are going to use one buffer. Okay, by using the buffer, the producer and consumer will do their works. Okay, here we have finite buffer pool. Okay, by using this finite buffer pool, we are going to exchange the message between producer and consumer. Okay, by here the size of the buffer is maximum size, there is no limit for the size of the buffer. So that's why we can say it is a bounded buffer problem. Okay, the solution for this bounded bounded buffer problem is we are going to create two counting way semaphores, that is full and empty, to keep track of the current number of full and empty buffers. Okay, this is a bounded buffer problem. Okay, so here in this second chapter we have studied about what is the process synchronization, how process synchronization works, so what is a critical section, see what are the four essential elements of critical section. So next one is what is a Peterson solution, what is a synchronization of hardware. Okay, so next one is what is a mutex lock. Okay, what is a semaphore, what are the two atomic operations of semaphore. So next one is properties, what are the various properties of semaphore. Next one is the types of semaphores. Next one is advantages. Next classical problems. Next one is among those bounded buffer. Next one is dining philosopher. So next one is reader writers problem. Next one is monitors, how the monitors will work, and finally what is synchronization examples. Okay, all these topics will comes under second unit, second chapter. Okay.